Well, so make sure that you know how to use a meter. Always check it on something to make sure it works before you start making measurements. And this just kind of goes through all the different types of settings. So you can go back and revisit this at any time. If you haven't used a meter and you forget what we were talking about, you can still take a look at this. This is pretty much how Ohm's law works. You can see up here with this diagram, the volts are the push, the amps are what's trying to move through the conduit, and the resistance measured in ohms is what's trying to restrict that whole process there. So how much gets through is just the balance between this and this. And over here, you see as the voltage goes up, so will the current. And we see if the resistance goes up, the current will go down. We also see the voltage across this resistor is going to follow the voltage changes in the power supply. Another representation showing flow. This represents current, and you got the force behind it. And here's the restriction that will regulate the flow. Ionization is that process of losing and gaining electrons. And we talked about the structure of an atom. We said the electrons have a negative charge. They circle about the center, the nucleus of the atom, and they can come off of their orbits. Typically, an atom is balanced. There's as many positive protons as there are negative electrons. So they balance each other out. If I lose an electron, a negative charge, that means what's left behind is more positive than it was. And the other thing would be if an atom picked up an electron, then obviously it's going to be more negative than it was. But in each of those cases, that process of losing and gaining electrons are called ionization. The covalent bonding is just where the attraction it's created, because now I've got a positive and a negative, they're drawn together. That's what causes like silicon to crystallize, other substances to crystallize. So you don't have all these atoms. What pulls them together? This type of bonding. This is one type of bonding. There's others, but that's what covalent bonding means. They're sharing the valence orbit. The idea of continuity, having a continuous path for flow. We see switches can interrupt continuity. It's like a drawbridge that stops the traffic. So I've got to have continuity for current to flow. Current has to flow through the load in order for the load to operate. Here you see it, up here you see the actual contacts in the switch that's doing the same thing as this here. All right, so simple Ohm's law. If I want to know what's the current flowing through here, everybody at this point should be able to tell me that, or to be able to figure it out. So because we go to Ohm's law, anytime I ask what's the voltage, what's the current, what's the resistance, Ohm's law is the go-to for that answer. So in this case, I want to know what current is. So I go over here, if I'm going to use this little cheat thing, and I can see that I is made up of power, square root of power over resistance. I can see that it's also the power divided by the voltage, and I can see it's the voltage divided by the resistance. Well, the only two variables that I have here, I don't have power as one of my variables, so that excludes these two equations as a possibility for use when leaving this one. So to get current, I divide the voltage by the resistance, as you see right here. So when I do that, divide 48 by 3 ohms, I get 16 amps. But what about the power? Well, I go up here to see what the power is, and I can see that if I have V and I can figure it out. Well, I do. Since this is just one element, I know that this whole 48 volts is across this. If I had two, then this voltage would be divided proportionally. But since I only have one, this gets the whole 48. Since I know this 48 volts and I also know 16 amps, I can calculate my power as V times I.
Yeah.
So we see that it's 768 watts. If I take the voltage and square it, divided by the resistance, then I still get 678 volts. If I were to take 16 and square it using this one right here, then I would get 768 watts. All right, so converting. In this case, I want to convert amps to kiloamps. It's something we didn't talk about in here. I'm going to talk about it briefly, and that's conversion factors. Because it's called a factor, it's something that we're going to be using to multiply by something else. And it's a conversion factor, so we're going to multiply something to get a conversion. And the way that it has to work is if I'm going to multiply something by something else, and I don't want to change the quantity of it, I just want to change the units, then anything I can multiply something by, a quantity by, and get the same quantity is 1, because 1 times any quantity is still that same quantity. So the conversion factor has to equal to 1. And the way that I do that is I set it up so that I have a fraction and that the quantity on the top and the quantity on the bottom of that fraction are the same quantity. That means it's equal to 1. If I have 5 over 5 or 6 over 6, any quantity over itself is equal to 1. So 1 kiloamp is the same quantity as 1,000 amps. So this conversion factor equals 1. This quantity is the same as this quantity. The way I set it up, how do I know which one to put on top? Because if I reverse these, it still equals 1. What I want to do is I want to have what I'm trying to get rid of on the bottom and what I want to keep on the top, so that when I multiply 1800 amps by this conversion factor, I get this, because the A's cross out, the kiloamps carry through. Same situation here. 1,000 millivolts is the same thing as 1 volt. So same process goes here. I can do this for gallons to liters, miles to kilometers, any conversion, as long as I set it up to putting what I want to get rid of on the bottom and carry through on the top, and make sure that the top quantity is the same as the bottom quantity. 50 hertz, kilohertz to hertz. Because these are two elements that are wired in series, then we know that the voltages, the source voltage, is divided proportionally among all of these. There's 2 of them. And because they're equal, and because it's proportional, this is a 1-to-1. So this is going to get half of it, and this is going to get half of it. They're going to divide it into 2 equal pieces. 1/10 apiece. Yes.
Mm-hmm.
What about the voltage across the fan?
480.
Why?
It's in parallel.
Good. What about this one? How many is across that R2?
10 volts.
10. That's right, 10.
Yeah.
Who said that?
Adam.
Okay. Yes. Divided proportionally. In this case, this gets 2 out of 3, and this gets 1 out of 3 parts. Remember that voltage divider rule. If you can go back and track that down, you can use that formula if it's something that's a little tough to do in your head. Okay, so here I want to know how much current is going through that monitor. Which one of these is going to have more current flowing through it, the projector or the monitor?
The projector.
Because
It has less resistance.
Yes. So because it has half the resistance, it'll have twice as much of the current. So in this case, this is going to get 2/3 of the current, and this will get the other third. All right, so here I'm asking how much power is being consumed here. And to do that, you have to use Ohm's law again, but you're going to have to know more than what you have here, because you can't use anything that has voltage in it at this point, because this 240 volts isn't over here. So I'm asking about power for R3. I have to use the resistance, the current, the voltage. I have to use all of those that's at R3. So I know the resistance here, but do I know the current? No, not right away. I can calculate the total current, and then I could use I squared times R. Or I could use the voltage divider principle, and then I could use V squared divided by R. So there's different ways you can go about doing it. Do what comes most natural to you, but make sure you have something to work with. 120, there's 60 volts across it, right? 60 squared divided by 10,000.
Oh, no, you did 60 squared, I did 240 squared.
So you can't use 240 squared because this
That's not an
240,
R3.
it's developed, yeah, that 240 is divided up among these three. So I'm seeing that these two are equal to this. So this is getting half, these two are getting half. That'd be 120 for each half, and then this is getting half of that, would be 60. So I get my 60 volts pretty readily because I've been doing this for a while, right? I might have just figured up the total resistance of this circuit and divided it into here to get the current, and then use the I squared times R. Again, do what works best for you, but just make sure whatever you're doing is right. All right, so here's that problem where one of the ratings of a battery is amp hours, and it tells you how long a battery is going to last in hours based on what the current demand is for the load, the amp hours. Amp hours, amps times hours. So in this case, this battery is 36 volts and it's rated at 60 amp hours. That means it can operate 60 amps for 1 hour. It can operate 1 amp for 60 hours, 30 amps for 2 hours, anything that multiplies out to 60. But in this particular case, 36 divided by 20, we're getting 1.8 amps. This load demands 1.8 amps. So we get 33 1/3 hours. Here's the one where the power company's charging me 13 cents per kilowatt hour. How much is it going to cost me to run this load for 24 hours? And here's what we have. Watts is V squared divided by R. So I get my watts. The power that's being used by this is 1200 watts, or since we want to know kilowatts times hours, it's 1.2 kilowatts. So this whole process should be pretty evident to you. Then we're going to multiply the kilowatts, because kilowatt hours is kilowatts times hours. We're going to multiply the 1.2 kilowatts by these 24 hours, and we get 28.8 kilowatt hours. Now the power company is charging me 13 cents for each one of them. So I multiplied 28.8 by, questions about that? Transformer problems, there'll be one of those on there, at least one. And make sure that you understand that the transformation ratio, they're talking about the number of turns in the primary compared to the number of turns in the secondary, because that's what makes this thing work, are those turns. That's something that you can't fool with, and it's probably something you need to know, at least basically that's why it's important. But what you're going to be, that's something you can't change. You know, that's just built into it when they make it. But something that you can use is that ratio also represents the voltage compared to this voltage. So if you know the transformation ratio, and I put a voltage on here, whatever voltage I put on here, I can tell what the secondary voltage is going to be because of that transformation ratio. And that's shown here, E1 over E2, which is the same as V1 over V2. But the current is the inverse. So remember that. Oh, let's just do one. My transformation ratio, I have at 2.5. That means on this side, I have 2.5 turns for every one over here. Maybe I have 5 to 2, but whatever the ratio is, it gets down to being 2.5 to 1, or you just say 2.5. Okay. All right. So if that's the case, and I know what voltage I'm putting on the primary, then I can calculate what the secondary voltage is. Because if I know what this is, transformation ratio, and I know what this is, then I've got two variables. I can figure out my third. So 2.5 is my transformation ratio. It's equal to E1 over E2. I know that E1 is this. So to solve for E2, I'm going to divide 150 by the transformation ratio, which is 2.5, and I get 60 volts. So the secondary is 60 volts. I want to know what's the current over here. The current on this side, Ohm's law, is going to be 60 volts divided by 2.2 thousand. And I get 27.3 milliamps. Okay, so now I can do, to find the current over here, I can do a couple things. I can calculate the power by using voltage squared divided by this, or I can use I squared times this. Whatever I want to do to calculate secondary power, knowing that a transformer has the same power on both the primary and the secondary, then I've calculated the power. I divide 150 volts into it, and I can get the current on the primary. Or now that I know this current for the secondary, I can go back to this equation and use alpha. The transformation ratio is equal to 27.3 over I1, and then solve that way. Here's another one where now this side, so the previous model, the previous version we looked at was a step down transformer. Here, apparently I have more windings on the secondary, so whichever side has the most windings also has the most voltage. So this is going to be a step up. I want to know the same thing, my current here, and I'll go through the same process, figure out my secondary voltage. And then divide resistance into the voltage to get the current. And then use the transformation ratio of 0.5 in this version of the equation to get the primary current. And to get power, I want to know the peak voltage for one. And I see that it's 1, 2, 3 divisions tall, but I don't know how far it is from here to here or from here to here. I don't know what 3 division means. How can I tell? I look over, huh?
On the side, I was going to say on the side.
Yeah. So here it's 0.5 volts, volts per division. So the volts, you have to know that volts is the up and down. And so 1, 2, 3 times 0.5 is 1.5, 1.5 volts peak. And RMS, if I'm asking for that, then you take the peak times 0.707 and you'll get the RMS value. Now, the frequency is hard to do without first doing the period. And so that's what we do. And when you're going to figure out measuring the period, Remember that you're just doing how long it takes for one cycle, not everything on the screen. So I don't want to start counting here unless I'm going to stop counting like here someplace. What I want to do is I want to take a point like from peak to peak, but I can't see this other peak, so that's not very good. So I'm going to take it at this crossover point. And one full cycle is from here to here. Maybe what messed some of you up is you weren't really clear what a cycle was. So make sure that that's clear, that it's from here to here. And now from there to there is 1, 2, 3, 4, 8 divisions. So how much is each division in time? I look up here, it's 10 milliseconds. So it's 80 milliseconds. The period is 81 thousandths of a second. Now don't get messed up here, because to find the frequency, you take the reciprocal of the period. You can't take the reciprocal of 80. You have to take the reciprocal of 81 thousandths. It's a big difference in quantity by 1,000. So what you would want to do, what's the easiest way to do is 80 milliseconds is 81 thousandths. So I would probably write 80 over 1,000. And then to get the reciprocal, I would write 1,000 over 80. And when you divide 1,000 by 80, you get 12.5, and that's expressed in hertz. Control circuit. This thing's going to operate like all logic. It's going to produce outputs based on the inputs and how it's designed, what logic is supposed to perform. So here are a bunch of switches and relays, and here are some conditions, and you're supposed to tell me if this is energized or not. If this is energized or not, this. In this particular case, this says limit switch 1 or 2 makes up whenever a gearbox is engaged in either high or low. So I've got a gearbox, and if it's in neutral, I don't want this thing to run. It's either got to be in high gear or low gear, or I don't want to even go any further. So I've got these switches that are on the gear selector. You know, it's like it's the switch that's just on your gear selector. When I put it in low, then this limit switch makes up and it says, okay, I'm in a gear. And if I put it in high, if I go to shift it in high, it'll come out of low and this will come back open. And when I get it into here, then I've got that to pick up. So I would say that if it's in gear, if it's in any gear, this is going to be picked up. The gearbox is in neutral. So if that's the case, this isn't picked up. So this is how it works. This is how the switches are set. This is the conditions right now, the present condition. So right now I would say, nope, that's not picked up. All right, what about down here? Level switch 1. Level switch 1 has to be adequate. And it says it's okay. Level in the tank is okay. So that's made up. But these are all in series. I've got to have all these made up. So that's made up. Flow switch 1. Flow switch 1 closes when I get my lube flowing to the pump, from the pump really, at 1.75 gallons per minute. So right now the lube is 2.6, which is more than that. So this is closed. This one's closed. Pressure switch. Whenever the pressure reaches 60 PSI, the pressure switch now is 62. So that's good. It's just like the pressure switch on your car. It makes the oil light come on. The thermal switch opens whenever the gears get over 225. So if the gears overheat to the point they get past 225, then this is going to open up and shut this thing down. This is for my fault stop. Any of these would be a fault condition if something wasn't right, and that's what makes this FSR come on. But the temperature is 110. So right now, these are all go, and FSR is picked up, energized. What about down here? Let's assume that I'm going to push the run button. And if FSR is picked up, we saw that it was, RG has to be picked up and it's not. So right now I know that it doesn't even matter about this because this isn't made up. There's no way that this could be made up. So FSR is picked up. Because FSR is picked up, this drops out, makes this go out, so this is off or de-energized. RR has to be on, and it's not, so this is not on either. Neither one of these lights are on. We talked a little bit about this. You may have to convert binary to decimal and decimal to binary, and this is the process for doing that. If I have 11010 binary, so 000 means I've got no, this is an 8-bit number. I've got no 128s, I've got no 64s, I've got no 32s, but I do have a 16, and I do have an 8. I have no 4s, I have a 2, and I have a 1. So you add all these up and you get 27. Converting this decimal or this binary to decimal yields 27. Makes sense? All right. Going the other way, if I want to convert 13 to binary, then I say, well, 128 go into 13, no, then put a 0. Will 64 go into 13? No, put a 0. Will 32 go into 13? No, put a 0. 16, no. 8, yes. So I put a 1. Then I subtract that. Now I subtract 8 from 13, I get a 5. Will 4 go into 5? Yes. And I subtract it and get a remainder of 1. Will 2 go into 1? No. Will 1 go into 1? Yes. And that's the process that's used for that. So,
Neat.
okay. And here are the gates. You need to make sure that you know the difference between an AND gate and an OR gate. OR gate means that if any of these are 1, you get a 1 here. An AND gate looks like this, and they all have to be 1 to get a 1 here. So here I've got a 1 because I've got 1 here, 0. 1 and a 0 going into an AND gate where they both have to be 1 to get a 1. They're not, so I get a 0. They all have to be 1 on an AND gate, so I've got a 0. But this is an inverter, which whatever goes in comes out the opposite. So now I have a 1. And here I've got a 0 and a 1. So it's going to be a 1. I've got a 1 to 1 on an AND gate. That'll give me a 1 on an output. So there'll be a couple of those to do.